So far, we've looked at how to solve a quadratic equation by graphing or by factoring. This particular quadratic is not factorable because there are no numbers that are going to multiply to the a times c value and add to the b value. But if we take a look at the graph, we can see that there are in fact two x-intercepts. If we go to get the value of those x-intercepts, they come out to be irrational numbers. So because not every quadratic equation is factorable, and because graphing may not give us those exact roots if they happen to be irrational, we can go about solving a quadratic by a third method, which is called completing the square. So we know that we used completing the square in the past to turn a quadratic in standard form into vertex form, and we know that this is the vertex form. If we're going to now turn this into a quadratic equation, so let's say in the place of a y, we have a 0, I can solve for what that x value is by rearranging that equation. We are not simplifying this, so don't start foiling. We're going to leave it in vertex form. We're going to rearrange. We're going to solve for x. All right, so our goal is to isolate x. We know we're going to do order of operations in reverse. So the first thing we're going to do is remove anything that we're adding or subtracting. So I'm going to bring this minus 2 to 0 by adding 2 to both sides. We're then going to remove any piece that we're multiplying or dividing. So I'm going to divide out this 4 from both sides. We're basically kind of working from the outside in. 4 divided by 4 is going to give me 1. And then I'm going to actually reduce this fraction. 2 divided by 4 is going to reduce to 1/2. Now we're going to get rid of any exponents. So we can get rid of a squared by square rooting. That's the opposite operation. And then we're going to square root the other side. When we square root, we know that a square root cancels a squared. And when we do this, because we have a variable here, we're going to end up with both a positive and a negative root. So as an aside, if I have x equals the square root of 9, then we generally give the principal root, which is the positive value of that root. If we have x squared equals 9, x can be either positive or negative 3, because positive 3 squared is 9, negative 3 squared is also going to give me 9. So square rooting will cancel the squared on the left, and then I'm going to have a positive and a negative root on the right because of that variable there. So I'm going to put a positive or negative sign in front of that root, and then I'm going to add 3 to both sides in order to isolate that variable. And when we do that, we end up with 3 plus or minus the square root of 1/2. When I added 3, I happened to put it in front of the square root. It doesn't matter if you want to put it at the end of the square root because we end up with one solution, 3 plus the square root of 1/2 and 3 minus the square root of 1/2. Here we have positive the square root of 1/2 plus 3, and we have negative the square root of 1/2 plus 3. So you'll notice that 3 minus the square root of 1/2 is the same as the negative square root of 1/2 plus 3. So we have successfully isolated x to get the two x-intercepts for that parabola. But remember, we don't like to leave a radical in the denominator. So we're going to go through the process of rationalizing the denominator just to clean this up. I know that I can break this square root of 1/2 into the square root of the numerator over the square root of the denominator. And then remember from last year that we are going to rationalize by multiplying by the square root of the denominator. So this has a value of 1. When we multiply by 1, we're not changing the question. And so now I can go the square root of 1 times the square root of 2 will give me the square root of 2 in the numerator. The square root of 2 times the square root of 2 gives me the square root of 4, which is 2. So I rationalize to get that perfect square in the denominator. So that's going to leave me with this value. And then also, if I want to combine these, right now my 3 is over 1. My lowest common denominator is 2. So we can go 3 times 2 will give me 6 in the numerator, plus that square root of 2 over the common denominator. You can always graph this on your calculator. So 6 plus root 2 equals divided by 2. 6 minus root 2 equals divided by 2. Those are going to be the exact values for those x-intercepts. Try a second one. So I have a quadratic equation in standard form. Let's see first of all if we can factor this. So 3 times 1 is 3. Are there two numbers that multiply to 3 and add to 6? No, this one isn't factorable. So what we're going to do first is complete the square square in order to get it into vertex form, where we can then quickly rearrange it in order to get exact values for those x-intercepts. So the first thing we do when we complete the square is we're going to divide that a term out of the first two terms. So we're going to end up with 6 divided by 3 is 2x, and then we're going to leave a space here. I'm going to take half of that b value, so 2 divided by 2 is going to be 1, and I'm going to square that. So we're going to add 1, and then right away we're going to subtract it so we don't change the question. This is going to give me my perfect squared trinomial. So then we're going to have 3 square root the first term, square root the last term, or you can also think about it as taking half of this term or square rooting this term. Either will work. And then we still have this 3 times negative 1 is going to be negative 3, and then we have that plus 1. So now let's go ahead and combine those like terms. And in vertex form, we're going to have 3 x plus 1 squared, negative 3 plus 1 is negative 2 equals 0. Now we have it really quickly into vertex form where we can rearrange this in order to isolate for x. In our first example, we went through every step so that you could see how we were doing this, but we can actually go from here directly into the final solution. So this is what I would do. I know I'm trying to isolate x. First thing we're going to do is move any piece that we're adding or subtracting over. So right away, I'm going to have positive 2, and then we're going to divide out the 3. So I'm going to say x equals, I'm going to leave a space, and I'm going to have positive 2 divided by 3. I know that I'm getting rid of a squared by square rooting. I know that when I square root, I'm going to have a positive and negative root. I'm going to get rid of this positive 1 by subtracting 1, and we have now got x isolated. So again, move over this piece, it becomes positive, divide out the 3, that gives us 2/3. Get rid of the squared by square rooting, we have the positive or negative root. We're going to move that positive 1 over, and it's going to become negative 1. These are the values of our two x-intercepts, but again, we don't want to leave radical in the denominator. So again, we're going to speed up this rationalization process. So to get rid of that radical in the denominator, I'm going to multiply that by the square root of 3 to get me that perfect square. And then we're going to have square root of 2 times the square root of 3 is the square root of 6. The square root of 3 times the square root of 3 is the square root of 9. Square root 9, we get that perfect square of 3. So we can quickly get that simplified. This negative 1 has the denominator of 1. I can take a look and say, okay, 3 is my lowest common denominator. I'm going to multiply the numerator by 3, and we're going to keep the denominator the same. So we're going to end up with negative 1 times 3 is negative 3 plus or minus the square root of 6, and those are our two x-intercepts. Now, if you are given the solution, can you work backwards to write the quadratic equation? Because we see a radical in each one of these, that's our clue that we're probably going to end up in vertex form. So the first thing we're going to do, working backwards, is we're going to isolate that radical. So in this case, my radical is isolated. There's nothing like there is in these examples where I'm adding or dividing anything to it. We're going to get rid of that radical by squaring both sides. So I'm going to square. Squaring is going to cancel the square root, and that's going to leave us just with that x squared is equal to 3. And then we're going to make this equal to 0. So if I want 0 on the right, I'm going to subtract 3, and then I'm going to do the same thing to the left side to keep it balanced. X squared minus 3 equals 0 is my equation. My vertex will be at 0, 3, which is going to be that y-intercept. All right, let's try the next one. So I need to isolate the radical. So I'm going to get rid of that 1 by subtracting it. I'm going to do the same thing to the other side to keep it balanced. I'm then going to get rid of that square root by squaring, and I'm going to square the entire other side. When I square something, it cancels out the square root, and that's going to leave us with x minus 1 squared. I'm going to bring this side to 0 by subtracting 5, and when I subtract 5, we're going to end up with our vertex form. The vertex is 1 and negative 5. Isolate the square root first. So in this last one here, I want to begin by getting rid of that divided by 2 on the denominator. So I'm going to multiply each side by 2, and then 2 halves is going to eliminate that bottom. And then we still need to get this radical isolated. So the next thing we're going to do is subtract 3 from each side. And then I'm going to eliminate that square root by squaring both sides. I'm going to now bring the right side to 0 by subtracting 7. And from those roots, we've now generated the equation in vertex form that would produce those intercepts. The last thing we're going to do is an application question. So we're given the dimensions of a picture, and we're told that we're going to crop that picture by removing the same width from all sides. So we're going to remove the same width from all sides. The first thing I want to do is kind of sketch this out to see what's happening here. So I've got my original picture, and if I'm cropping it, I'm going to use the same variable to indicate that that is the amount that we're removing. And we're also told that it's going to reduce the area by 40%. So we can determine what the original area is by multiplying the length and the width together. And then if we reduce that area by 40%, it means we're going to keep 60% of this amount. So let's multiply that by 0.6. And our new area is going to be 432 square centimeters. Now we can set up an equation because we know that our length, our new length, is going to be 30. So we take this original and we subtract 2x from it. Our new width is going to be the 24, subtract those 2x to get that side. So those together, when they're multiplied, length times width will give us that new area. We now have a quadratic equation where we can go ahead and solve for x. And then let's FOIL this out to put this in standard form. So we're going to multiply 30 times 24 to get 720, negative 60x, minus 48x is going to give us that middle term of negative 108x, and then negative 2x times negative 2x is positive 4x squared. I'm now going to move over this 432 to bring my one side equal to 0. And then once we do that, we end up with this. Our ultimate goal is to solve for x. If the question does not say you have to do it algebraically, you could always graph it and get those x-intercepts. You can also remove a greatest common factor of 4 and then see if this is factorable. But because we're working on solving a quadratic by completing the square, I'm going to just walk you through that process. So I'm going to divide a 4 out of those first two terms here. And when we do that, the coefficient on that x term is negative 27. Negative 27 divided by 2 and then square that value gives us that 182.25, which we then automatically subtract. This gives us our perfect square trinomial. So we go ahead and factor that, and then just remember we're going to go 4 times that negative 182.25 to get negative 729, and then we're going to combine that to 288, and we now have a quadratic equation in vertex form. I'm solving for x. So I'm going to begin by moving over 441, dividing by 4. 441 divided by 4 is 110.25. We're going to square root to get rid of that squared, and then we're going to move over that 13.5. 110.25 is a perfect square, so I can go ahead and square root that. This also tells me that this would have been factorable. And then we have two solutions. We have 13.5 plus 10.5, which is going to give us 24. And then we have 13.5 minus 10.5, which is going to give us 3. Now, go back to what ultimately x represents. X is the width of the strip removed. These two solutions are mathematically correct. We can substitute them back into the original equation and verify that. But does it make sense for x to be 24 centimeters if the entire width of the rectangle is 24 centimeters? Clearly not. So we call that 24 an extraneous root, which means the solution has to be 3. It does make sense to remove 3 centimeters along each side. So in this particular context, our solution is going to be 3 centimeters removed from each strip.